think about this for a second. You're trying to navigate rush hour, right? But your GPS suddenly starts spitting out garbled directions.
Yeah, the voice crackles, the map freezes.
Exactly. And those clear instructions just become this jumbled mess. What happens then?
Well, you're essentially blind, stuck trying to find an open lane on a crowded highway, but your most critical guide has gone silent, or, worse, is actively misleading you.
That's a really powerful way to frame it, actually, because it perfectly captures, a fundamental challenge in our wireless world today.
We have these incredibly valuable but finite resources, the radio frequency spectrum,
Finite, yeah.
but so much of it remains stubbornly underutilized. It's like having these vast open stretches of a digital superhighway just sitting empty while other parts are completely gridlocked.
And a big reason for that inefficiency.
It's that our current communication systems often struggle to reliably identify those open lanes, those opportunities.
So how do we fix that? How do we get our digital GPS back online, clear and precise?
Well, that's exactly what we're diving into today.
Right. Our focus is on a really fascinating and frankly cutting-edge technique. It's known as Cooperative Wideband Spectrum Sensing.
Which is a vital component of something bigger called cognitive radio.
Yeah. And our mission, if you will, is to really get our heads around the monumental challenge of finding these free radio frequencies.
And to understand how existing systems are trying to solve it. And maybe most critically,
how we can make those solutions actually work even when the very information channels we rely on are themselves unreliable or, prone to errors, just noisy.
We're going to unpack some really insightful research. It's from a paper by Kamal Captain, published in Wireless Networks, that tackles these exact issues head-on.
It sounds like it.
Indeed. And the core question we're wrestling with today is pretty profound, really. How do we unlock the hidden, massive potential of our radio spectrum for all these new, groundbreaking applications?
Without causing disruptive interference to those who already legitimately use it. That's the key, isn't it?
Yeah. That's the absolute key. And how do we do that, especially when the crucial signals we rely on to make these decisions might be corrupted or noisy?
It sounds incredibly complex.
It is a complex problem, as you said, but the solutions we'll explore today are surprisingly elegant in some ways.
Okay, so let's start at the beginning, because understanding the problem is really at the heart of why this research is so impactful, right?
Absolutely.
When we talk about the radio frequency spectrum, we're talking about, as you said, a finite, precious resource.
Think of it like prime real estate. There's only so much land available to build on, only so much space in the airwaves.
And for decades, this digital land has been divided up and parceled out through a system known as static licensing.
That's a great analogy of the real estate one. Because static licensing really does create this kind of rigid, inflexible zoning plan for the airways.
Right.
Large chunks of this incredibly valuable spectrum are exclusively allocated to specific users or services, often with very little dynamic adjustment needed or possible.
Like old TV broadcast bands or something.
Exactly. Think legacy broadcasters, radar systems, even some older cellular bands. These entities have licensed rights to specific frequencies.
Okay.
The challenge arises because these licensed users, we tend to call them primary users, or PUs, they aren't always actively transmitting.
Ah, okay. So they own the rights, but they're not using it 24/7.
Precisely. They might use their assigned frequencies only intermittently or maybe only in certain geographic areas.
Which means?
Which means for significant periods of time or in various locations, vast stretches of that digital highway you mentioned are sitting completely empty while other parts are absolutely gridlocked with traffic.
It sounds like more than just inefficient. It feels like a colossal waste.
It really is. Study after study, actual measurements of the RF spectrum consistently show that many of these licensed bands are heavily, sometimes shockingly, underutilized.
And when you think about how costly this resource is, how much companies pay for licenses, the infrastructure.
Exactly. This underutilization represents a massive economic and technological inefficiency.
Especially now, right, with this explosion of new wireless applications.
Absolutely. From the Internet of Things, the IoT, where countless sensors and gadgets need to communicate seamlessly,
to the foundations for the next generations of wireless, like 5G, 6G, whatever comes next.
All of these innovations are desperately vying for space on this limited digital real estate, yet so much of it is just sitting idle.
Okay, so that's the problem. Scarcity combined with waste.
And this inherent problem of spectrum scarcity, coupled with that observed underutilization, is precisely where cognitive radio, or CR, steps in as an incredibly promising solution.
Cognitive radio. Okay.
Instead of relying on those static, rigid allocations, CR offers a dynamic, intelligent approach. It essentially allows unlicensed users—
We call those secondary users, right? SU.
that's right, secondary users, SUs— it allows them to opportunistically and intelligently use the spectrum belonging to those licensed primary users.
But only when those PUs are not actively transmitting. That's the critical part.
That is the absolute critical part.
So it's like those smart, maybe autonomous cars we imagine in the future, dynamically finding open lanes on our digital highway without needing a human to tell them where to go.
That's a good way to think about it. They just sense the opportunity and act.
But here's the crucial catch, the pivotal requirement. For cognitive radio to actually work, for these secondary users to be truly smart and opportunistic.
They absolutely must be able to dynamically find these empty PU bands in real time.
And this dynamic detection process, that's what we call spectrum sensing.
Exactly, spectrum sensing. And crucially, this isn't just about finding an empty spot. It's about a highly sensitive, almost respectful form of sharing. Meaning the fundamental requirement here is that these secondary users must operate on a non-interference basis.
Non-interference, got it. So no stepping on toes.
Zero stepping on toes. This means if a primary user, say a vital emergency service or maybe a critical communications link, suddenly reappears and needs its licensed band back,
The secondary users have to get out fast.
immediately, they must detect that presence instantly and vacate that band without delay. This demands incredibly powerful, rapid, and most importantly, supremely reliable sensing techniques.
To ensure those PUs are never, ever disrupted.
Never. It's a very delicate and essential balance. Maximizing spectrum utilization while rigorously protecting the rights and operations of the primary licensed users.
Okay, so spectrum sensing is mission critical. But then we hit another layer of complexity, don't we? This spectrum hole challenge.
Yes. You see, primary users typically don't just occupy an entire wide swath of spectrum like one giant contiguous block.
It's not that simple.
No. More often, they might only be using a small, specific portion of their allocated band at any given time. This creates multiple, often scattered, spectrum holes or opportunities across a broad range of frequencies.
Like your highway analogy again, the main traffic isn't using lanes 1 through 8. They're using lane 1, then jumping over to lane 7, then maybe lane 12 way down the line.
Exactly. There are still plenty of empty lanes, but they're not all conveniently clumped together.
Which means we can't just look for one big open channel.
Precisely. We need techniques that can survey a broad range of frequencies simultaneously, identifying all those individual scattered holes.
And that leads us to wideband spectrum sensing.
That's the term. The ability to scan, analyze, and identify opportunities across a much wider frequency range quickly and efficiently.
And to really supercharge this capability, to maximize throughput for those secondary users, while rigorously minimizing interference to the primary users.
Researchers propose something quite brilliant: Cooperative Wideband Spectrum Sensing, or CWSS.
Cooperative, so working together.
Exactly. This algorithm doesn't rely on just one secondary user trying to find these holes in isolation. Instead, it leverages a combination, usually a linear combination, of local statistics gathered from several cooperative secondary users, or CSUs.
Okay, but break that down. Local statistics.
Think of it like a highly coordinated team of scouts. Instead of one scout trying to map an entire vast, complex area alone, you deploy a whole team.
Makes sense.
Each scout scans a small, manageable part of that area, collecting their individual observations and insights. Those are their local statistics.
Right.
Then, they mathematically combine these individual readings, essentially averaging their best guesses, or using some other smart combination rule to construct a complete high-resolution picture of the entire territory.
So collective intelligence.
Exactly. This shared sensing is far more powerful and reliable than any single scout could achieve on their own. It significantly reduces the chance of any one scout making a mistake or maybe missing a critical detail.
That collective approach makes a lot of sense. Now, before CWSS really took hold, I gather there were other approaches.
Oh, yes. And while innovative, they all face some significant limitations. Early CWSS algorithms, for instance, focused on combining those local statistics or using some pretty advanced techniques like expectation maximization.
Okay.
Then came things like over-the-air computation for CWSS, OA CWSS. This tried to use the superposition property of wireless channels to directly combine signals in the air.
That sounds clever, but tricky.
Very tricky. It sounded clever, but it ran into major issues. Problems like needing really high bandwidth for the feedback channel to coordinate things, and dealing with incredibly difficult synchronization offsets.
Synchronization, meaning
You know,
timing issues.
exactly. If signals arrive at slightly different times, or even with slightly different frequencies, even tiny mismatches can completely scramble the combined message. Think of trying to conduct an orchestra where every musician's watch is just a fraction of a second off. Total chaos.
Okay, so OACWSS had problems. What else?
There was also an approach using fast Fourier transforms, FFTs, with one-bit quantization. One-bit FFT CWSS.
1 bit. That sounds very compressed.
It is. It aimed to estimate the power spectral density of the wideband signal using the FFT of these heavily quantized streams, but a common thread among most of these prior techniques, and a major limitation for wideband sensing in general.
Was there reliance on something called Nyquist sampling to acquire the wideband signal?
Right. And here's where we hit a significant engineering bottleneck.
The sampling rate.
Yes. The absolute need for very, very high sampling rates, often at that Nyquist rate, to capture all the information in a wideband signal without distortion.
And high sampling rates mean?
They translate directly into significant computational intensity, needing powerful processors, massive data handling, and it drives up the implementation costs dramatically in real-world hardware.
It's expensive and complex.
Very. Imagine trying to capture every single ripple and current from a massive, fast-moving river. It's incredibly demanding on your sensors and your recording equipment.
So people tried to get around this.
They did. Algorithms like compressed sensing or CS were proposed. These promised a really elegant theoretical solution, overcoming the high sampling rate issue by sampling at sub-Nyquist rates.
Taking fewer samples, basically.
Fewer, but more strategic snapshots of that river, yet still being able theoretically to reconstruct the full picture. But while theoretically sound and powerful in concept, in practice, these CS-based algorithms generally prove to be quite complex computationally and, again, expensive to implement. This made them less practical for widespread adoption, especially in resource-constrained cognitive radio devices.
Okay, so high sampling is hard, compressed sensing is complex. What's the breakthrough?
The breakthrough came from a really crucial insight, a shift in perspective. Cognitive radio users, those secondary users, they aren't necessarily interested in finding all possible spectrum opportunities across the entire wideband.
Right, we talked about that. They
Yeah.
just need enough.
Exactly. Often they just need a sufficient number of them to operate enough open lanes to keep their traffic flowing smoothly. This realization led to a brilliant idea. Partial band Nyquist sampling, or PBNS.
Partial band. Okay, so sampling just part of it.
Precisely. The elegance of PBNS lies in its targeted approach. Instead of trying to sample the entire vast frequency range, it samples only a part of the wideband, specifically what's called the partial band.
And that single change is transformative.
Absolutely, because it drastically reduces the required sampling rate. Since you're only looking at a smaller slice of the spectrum, the Nyquist rate for that slice is much, much lower.
Okay. It's like instead of mapping every single inch of the highway, you strategically focus only on the most promising sections where you expect to find open lanes.
That's a perfect analogy. Maybe focus where historical data suggests they're most likely to appear. This drastically cuts down on the effort and resources needed for sensing.
So how does this actually work in practice? Let's look at that specific algorithm, centralized PBNS CWSS from the paper.
Okay. In this setup, you have multiple cooperative secondary users, CSUs, maybe M of them. They're all listening in on a wideband signal that contains a total pool of D channels.
Right.
Each of these MCSUs then intelligently filters out a specific partial band, a smaller, more manageable slice of, say, L channels from that wider D channel spectrum.
So L is much smaller than D.
Usually, yes. They don't try to listen to everything. They focus on their assigned portion, their L channels. They then sample this filtered partial band at its own, much lower Nyquist rate.
Because L is smaller.
Exactly. Because they're only focusing on a small part of the highway, the amount of data they need to process is drastically reduced. This makes it far more efficient for each individual CSU.
What happens after sampling?
The sample data then goes through a fast Fourier transform, an FFT block, which is a standard signal processing tool to analyze the frequencies present within that partial band.
Okay.
And crucially, each CSU calculates a decision statistic for each of the L channels it's looking at. This is often just the energy level in that channel.
Low energy means probably free. High energy means probably busy.
That's the basic idea. A low energy level typically suggests the channel is unoccupied, while high energy suggests a primary user might be active there. This energy level helps them determine if a channel is potentially free.
And this is where the cooperative part really comes in, right? With this hard combining at a central fusion center, the FTC.
Yes. The CSUs don't send all their raw, bulky data back to the FC. That would just swamp the network, too much bandwidth needed.
Too inefficient.
Very. Instead, each CSU processes its own local readings and makes its own initial binary decisions on those L channels it's scanning if it detects a channel as potentially free.
It sends just a simple message.
It converts that channel number into a concise binary form, maybe a short LM-bit binary number, and sends only that compact binary decision, that vote, to the fusion center.
That's the hard combining part. Sending the decision, not the raw data.
That's right. It's a smart trade-off. By sending only the final decision, essentially a, yes, I think this channel is free, or maybe just the number of the channel it thinks is free rather than raw measurements, it drastically reduces the amount of information that needs to be transmitted back.
Which saves that precious reporting channel bandwidth.
Exactly. And it speeds up the entire decision-making process. It's not about sharing every detail of the scout's observation, just getting their clear vote on whether a specific path seems open.
Okay, so the fusion center gets all these votes. What does it do?
The decision-making process at the FESC is where all these individual votes come together. Once the CSUs have scanned their partial DENs and calculated their energy levels, they typically arrange their decision statistics in ascending order lowest energy to highest.
So the most likely free channels are ranked first.
Correct. Each CSU then identifies its most promising few channels, let's say the top X channels that it individually believes are truly free based on its readings.
The ones with the lowest energy.
Usually, yes. When a CSU identifies one of its X promising channels as free, it reports that specific channel number to the fusion center using that LM-bit binary representation we mentioned.
And the fusion center acts like the campaign headquarters, tallying the votes.
That's a good way to put it. It acts as the central intelligence hub, collecting all these reported channel numbers from all the CSUs. It decodes the incoming binary numbers. And then, very intelligently, it counts how many times each specific channel is reported as free by the various CSUs. Finally, it organizes these channels in descending order based on how many free votes they received.
Now, there's a key parameter here, right? FD.
Yes, FED. This is essentially a confirmation threshold. It's the minimum number of times a particular channel needs to be reported as free by the CSUs for the fusion center to actually declare it free and ready for use by secondary users.
Like needing a certain number of scouts to agree before you trust their report.
Precisely. It adds a critical layer of reliability and helps prevent false positives, situations where a channel is declared free but actually isn't.
Can we walk through a quick example?
Sure. Let's take a simple case similar to what's in the paper. Imagine we have M3 CSUs in our cooperative network.
Okay, 3 scouts.
And the Fusion Center's goal is to identify just one truly free channel for secondary users to use, so LD1, SD1. And let's say each CSU just reports its single best candidate, so XD1.
Right. We need that confirmation threshold, FD.
Let's set F to D to 2, meaning at least 2 different CSUs must independently report a channel as free for the FD to declare it truly open.
Okay, F to D is 2.
Now let's say CSU1 reports that channel 3 is free. CSU3 also reports that channel 3 is free.
So channel 3 has 2 votes.
Correct. But then CSU2 reports that channel 4 is free.
Only 1 vote for channel 4.
In this simple counting scenario, yes. So the FTC counts the reports. Channel 3 was reported free twice. Channel 4 was reported free once. Since channel 3 meets the FD2 threshold, the Fusion Center declares channel 3 free.
Makes sense. What if, say, channel 3 got 2 votes and channel 4 also got 2 votes?
Good question. If multiple channels meet the FD2 threshold with an equal number of confirmed free reports, the FTC would typically just select one of them with equal probability. The main goal is fulfilled, finding a confirmed free channel.
Okay, this whole system, the cooperative sensing, partial band sampling, hard combining, the confirmation vote, it sounds incredibly robust, almost foolproof.
It sounds that way, doesn't it? And indeed, many previous studies on this topic, including that foundational PBNS-CWSS algorithm the paper builds upon, made a crucial simplifying assumption.
Uh-oh, what was it?
They assumed error-free reporting channels.
Ah, meaning the votes always get through perfectly.
Exactly. They assumed the information from the CSUs reached the fusion center perfectly, unaltered, without a single bit getting flipped or lost in transmission.
Which, in the real world,
Is almost never the case. In an ideal, pristine lab environment, maybe. But here's the Achilles heel, the big, messy problem that trips up so many elegant theoretical solutions.
the reporting channels aren't perfect.
Not even close. In the real world, those reporting channels connecting the CSUs to the fusion center are wireless channels. And wireless channels are inherently, notoriously, incredibly susceptible to all sorts of impairments.
Like what?
We're talking real-world physics here. There's path loss, where the signal simply weakens over distance, like trying to hear someone shout from across a massive field. Then there's multipath fading. The radio signal bounces off buildings, hills, even trees sometimes, arriving at the receiver via multiple paths.
And those paths interfere.
They interfere with each other, sometimes constructively amplifying the signal, but often destructively, canceling it out, leading to sudden, deep signal drops or fades.
And shadowing.
That's when physical obstacles, like dense buildings in a city or even just hilly terrain, completely block or severely weaken the signals.
So that assumption of perfect reporting channels.
It simply does not hold in any practical real-world deployment. The information that the CSUs collect and then transmit to the fusion center is highly susceptible to corruption by all these wireless effects.
Which means errors in the final decision.
Exactly. This corruption can, and often does, lead to significant errors at the fusion center. If the FTC mistakenly thinks the channel is free when it's actually occupied by a primary user,
That causes harmful interference, the cardinal sin.
precisely. Conversely, if it thinks the channel is busy when it's genuinely free, that's a missed opportunity to use valuable spectrum, leading right back to that problem of underutilization we started with.
So the reporting channel itself is a major vulnerability. How do we model these errors?
To understand and rigorously model them, researchers commonly use a concept called the binary symmetric channel, or BSC. It's a fundamental model in communication theory for analyzing the reliability of a digital link.
A binary symmetric channel, BSC. How does it work?
It's pretty straightforward conceptually. You transmit a binary digit, a 0 or a 1, but there's a certain crossover probability, usually denoted as P, that this bit will be flipped when it's received.
Flipped. 0 becomes 1, or 1 becomes 0.
Exactly. If you send a 0, it might arrive as a 1 with probability P. If you send a 1, it might arrive as a 0 with the same probability P.
And the chance it gets through correctly.
That's simply 1P.
Okay, so P represents how noisy the channel is?
In essence, yes. And the consequences for our cooperative wideband spectrum sensing system are pretty significant. When those CSUs transmit their crucial channel numbers, which are converted into these binary packets to the fusion center,
Those noisy channels can flip bits.
they can and they do. Imagine a channel number was transmitted as, say, binary 0001, representing channel 3. Because of a flipped bit somewhere in that sequence, it might be detected at the FC as 00001.
Which is channel 1.
Exactly, a completely different channel. This subtle error clearly leads to incorrect decisions about spectrum availability, undermining the entire system's reliability and its core mission of avoiding interference.
So the big question becomes, how do we build resilience into this critical reporting channel? How do we make sure those votes from our scouts are heard clearly, even through all the static and noise?
This is where we turn to the brilliant field of error-correcting codes.
Coding to fix the errors.
Precisely. To combat these real-world channel abnormalities, the path loss, the fading, the shadowing, the resulting bit flips, error-correcting codes become absolutely vital. They are specifically designed to detect and, crucially, correct bit errors.
Improving the overall system performance.
Significantly, making it robust against the inherent imperfections of wireless communication.
So what's the first approach the paper looks at?
The first, and perhaps most straightforward approach explored is something called the repetition code-based CWSS, or RePC-CWSS.
Repetition code. Sounds simple.
It is perhaps one of the simplest error-correcting codes you can imagine. The concept is incredibly intuitive. Each binary digit in the message is simply repeated a certain number of times, let's say R times, before it's transmitted over that noisy channel.
So if R is 3 and I want to send a 1?
It doesn't just go out as 1. It gets encoded and transmitted as 1111. A 0 would become 1000.
Yeah, simple enough. How does it help?
The genius, or maybe just the simple effectiveness, comes at the receiver, in our case, the fusion center. There, a majority decision rule is applied to each group of R received bits.
Majority rule.
Yeah. Sticking with our R3 example, if the fusion center receives, say, 101,
Two ones and 1 0 away.
right, the majority of the bits are 1. So the system confidently infers that the original transmitted bit was most likely a 1.
Even though one bit got flipped by noise.
Exactly. This simple redundancy helps recover the transmitted message even if one, or sometimes more depending on R, bits within that repeated group got flipped due to channel noise. It's like asking 3 people the same question, and if 2 agree, you generally go with their answer.
Okay, so how does this plug into the CWSS system?
The initial process at each CSU remains pretty much the same. They do their partial band Nyquist sampling, figure out which channel numbers they think are free based on energy levels.
Then they convert those numbers to binary, the LM bits.
Correct. But before they transmit those bits to the fusion center, each individual binary bit, each 0 or 1, is repeated R times.
Got it. So the FC receives these longer, redundant streams.
Yes, from all the CSUs. It then diligently applies that majority rule to decode each group of R received bits, reconstructing the original channel number bit by bit.
Hopefully correcting errors along the way.
That's the goal. Once it has these reconstructed, hopefully error-corrected channel numbers from all the cooperative secondary users, it proceeds just as before.
Counting the votes for each channel, checking against VESI.
Exactly. It counts how many times each particular channel is reported free and makes the final decision based on that FD confirmation threshold. It's the same aggregation process, but now ideally with much cleaner, more reliable input data.
Can we use that example again to see how it works with errors?
Let's try. Imagine we're representing channel numbers with 4 bits, so LM4. We choose a repetition length, R3, and our confirmation threshold, FD, is still 2.
Okay, LN4, R3, FD2.
Let's say CSU1 detects channel 3 as free, which is 0011 in binary. It transmits 00 for the first 00 for the second 0, 111 for the first one, and 111 for the second one. That's 12 bits total set. Right. If the fusion center receives 1,111,111, a perfect transmission, no errors, it applies majority rule to each group, decodes it perfectly as 0011, which is channel 3, no problem.
Okay, now add some noise.
Now here's where the error correction shows its power and maybe its limits. Let's say CSE2 detects channel 5 as free, which is 0101 in binary. It intends to transmit 111,111.
Okay.
But imagine the wireless channel is particularly nasty for that transmission and several bits get flipped. Maybe the FEC receives 010, 101, 001, 110. Looks like quite a few errors there.
Yeah, quite a few flips. How does majority rule handle that?
Let's see. First group, 010, majority is 0. Second group, 101, majority is 1. Third group, 001, majority is 0. Fourth group, 110, majority is 1.
So it reconstructs 0101.
Exactly. Even with 3-bit errors scattered across the transmission, one in the first group, one in the second, one in the fourth, the majority rule correctly decoded each original bit. It reconstructed 0101 channel 5.
Wow, so it worked perfectly, even with multiple errors.
In that specific example, yes. It shows how robust Argyle 3 can be against single-bit errors within each block. Now, if 2 bits got flipped within the same block of 3, say 111 was received as 100, then majority rule would incorrectly decode it as 0.
Okay, so it can correct 1 error per block, but not 2.
For R3, that's correct. It highlights both the success in correcting many common error patterns and its vulnerability. If the noise is so bad, it flips multiple bits within a single small block. It's very effective, but not entirely foolproof against extreme noise bursts concentrated in one spot.
Still, that seems pretty powerful for such a simple scheme.
It really is. The primary advantage of REPC CWSS is its sheer effectiveness at reducing errors. The research paper rigorously demonstrates this. In fact, a truly remarkable finding they highlight is that by properly choosing the repetition length R,
You can make the errors disappear.
essentially, yes. The negative effects of reporting channel errors can effectively be eliminated. This is a huge potential breakthrough for reliable spectrum sensing in the messy, real world. Imagine driving on a road full of potholes, but your car now magically floats right over them.
That's the level of reliability this simple repetition trick can offer,
Yeah.
making that noisy channel seem almost perfect.
That's what the analysis suggests is possible, making what was previously a critical vulnerability almost a non-issue if you choose R appropriately.
Okay, that is genuinely stunning, making the noise problem basically vanish with simple repetition. But
Hmm.
There's always a but in engineering, isn't there?
There usually is.
Hmm.
This significant benefit comes at a cost. RepCCWSS suffers from a low information rate due to the high redundancy.
Right. All those extra repeated bits.
Think about our example. To send just 4 bits of information about the channel number using R3, you have to transmit 12 bits. 8 of those bits are entirely redundant, just there for error correction.
That's a lot of overhead.
It is. This demands significantly higher reporting channel bandwidth. You need a wider pipe for the communication between the CSUs and the FCC, and it naturally increases the processing time, the sensing time at the fusion center, as it has to handle and decode all that extra repeated data.
So repetition codes, super effective at fixing errors, but really inefficient with bandwidth and time.
That's the trade-off, exactly. While undeniably effective at making the reporting channels robust, their inefficiency is a major drawback, especially in bandwidth-constrained wireless environments where every bit truly counts.
Which leads us to look for something better.
It leads us to a more advanced and, frankly, more elegant solution that addresses this inefficiency directly: the Hamming code-based CWSS, or HAMC CWSS.
Hamming codes, I've heard of those. They're more sophisticated.
Much more. The genius of Hamming codes is that they directly tackle the high redundancy problem of simple repetition codes, offering a far more efficient way to achieve error correction.
How do they work, basically?
Hamming codes are a type of block code. They add a minimal number of intelligently calculated parity bits. Those are the redundant bits specifically designed to support error detection and correction without simply repeating everything. They encode LM message bits.
Our original information, the channel number bits.
Into a slightly longer LC code word. These are generally denoted as LCLM codes.
Okay, LC is the total length, LM is the useful information.
Correct. A widely used and very practical example is the 7-4 Hamming code.
7 and 4. Meaning,
And it encodes 4 message bits, LM4, into a code word of total length 7, LC7.
so it only adds 3 extra bits.
Exactly. It only adds LP LMN equals 7, 4 equals 3 parity bits.
Wow. Compare that to the repetition code. For those same 4 message bits, ARCA3 repetition needed 8 redundant bits.
It's a striking difference in overhead, isn't it? 3 parity bits versus 8 redundant bits. Huge efficiency gain.
What can it correct with just 3 extra bits?
And this is key. Hamming codes, specifically the standard ones like 7-4, are designed to detect up to 2-bit errors and, crucially, correct 1-bit errors within that block of 7 bits.
Correct single-bit errors. That might sound limiting, but
But in many wireless scenarios, single-bit flips caused by noise are actually the most common type of error. Hamming codes handle these with remarkable efficiency, far superior to the brute force repetition approach for correcting those single-bit errors.
it's like setting a postcard comparison again. Repetition sends 3 identical postcards. Hamming sends just 1 postcard but adds a tiny, clever-coded stamp that lets the post office fix any single smudge it finds.
That's a fantastic analogy. Which one is cheaper and faster to mail? Clearly, the Hamming code postcard.
The efficiency numbers must be dramatic then.
They are. For that 4-bit channel representation, repetition code R3 needs 8 redundant bits. Hamming code 7 and 4 needs only 3 redundant bits. Massive improvement.
And if you need to send multiple channel numbers.
Let's say a CSU needs to report 5 potential channel numbers to the Fusion Center. With RepC CWSS R3, transmitting those 5 numbers, each 4 bits, would require 8 equals 40 redundant bits in total.
Okay.
With HAMC CWSS, using the 7-4 code, transmitting those same 5 numbers would only need 3 equals 15 redundant bits.
15 versus 40.
Exactly. That makes HAMC CWSS, in this specific comparison, 166.66% more efficient purely in terms of redundancy. It's a huge saving.
So how does HAMC CWSS fit into the overall system? Is it similar to RepC?
The integration is quite similar conceptually. The CSUs detect the free channel numbers, convert them to binary LM bits, but instead of just repeating the bits,
They apply the Hamming encoding algorithm to generate the LC bit code word.
correct. This slightly longer code word is then transmitted over that potentially noisy reporting channel.
And at the Fusion Center.
The FDIC receives the LC bit code word and applies the Hamming decoding algorithm. This algorithm can detect if errors occurred and, crucially, correct any single bit error within that block.
Giving it back the original LM bits, hopefully error-free.
Ideally, yes. Once the FC has these decoded, error-corrected channel numbers from all the CSUs, it proceeds just as before. Counts the reports for each channel, compares against the Fed threshold, and makes the final decision.
So the benefits seem really clear.
They are compelling. ham-CCWSS drastically reduces the number of redundant bits. This translates directly into lower reporting channel bandwidth requirements,
You need a smaller, more efficient pipe for that control channel chatter.
which frees up valuable spectrum for actual data transmission by the secondary users. It also enables reduced sensing time at the fusion center because there's simply less data to decode and process compared to high repetition codes.
Okay, less bandwidth, faster processing. But what about performance? Does it correct errors as well as the repetition code?
And here's the truly crucial part, the clincher really. The paper shows that in terms of performance, how well it corrects errors and helps the system find free channels while avoiding interference, ham-CCWSS performs almost identically to rep-C-CWSS with R3,
Wow, so you get basically the same amazing error correction capability.
but with dramatically better efficiency. As we noted earlier, rep-C-CWSS with R3 was incredibly effective, almost eliminating channel errors. ham-CCWSS achieves very nearly that same level of robustness.
Which makes Hamming codes.
The far more practical and better suited solution for real-world cognitive radio systems, it offers the best of both worlds. The strong error correction needed for reliability combined with the efficiency needed for practicality. It's the clear winner for widespread deployment in many scenarios.
Okay, so we've got the problem, the basic PVNS solution, and now these error-correcting codes, rep-PC and ham-C, to make the reporting robust. How do we actually measure the success of these new algorithms? How do we prove they're better?
That's a really important question, especially in the nuanced context of wideband spectrum sensing, because traditional metrics often used in wireless communication, things like mean square estimation error, MSE, or even the classic probability of false alarm, PF, and probability of detection, PD, they aren't always the best fit here.
Why not? PV and PV sound pretty relevant.
They are, but the goal of wideband spectrum sensing is fundamentally different from, say, a system trying to detect a single radar pulse with absolute precision. Remember, secondary users might only need some spectrum opportunities, not necessarily all of them, to function effectively.
Right, they just need sufficient open lanes.
Exactly. This means WSS can actually tolerate a somewhat higher false alarm rate, occasionally thinking a channel is free when it's busy, compared to a system where any miss or false alarm is catastrophic. The traditional metrics don't fully capture this specific requirement for sufficient opportunities while still protecting the primary users.
So we need different metrics.
This crucial need led researchers, specifically Sun and Leineman in an earlier work cited by this paper, to propose new, more suitable metrics specifically tailored for wideband spectrum sensing.
Okay, what are they?
The first one is the probability of insufficient spectrum opportunity, or PISO.
PISO. Probability of insufficient spectrum opportunity.
Right. This measures the probability that the number of successfully identified off of channels that are genuinely free and correctly identified, falls below a required threshold, which they call SD.
SD being the number of channels the secondary user actually needs.
Precisely. So PISO SD is basically the probability that PRS SD, where S is the number of successfully found free channels, it directly addresses the user's need for sufficient opportunities. It asks, are you getting enough of what you need to operate?
Okay, that makes sense. What's the other metric?
The second one, equally vital, focuses on the other side of the coin, protecting the primary users. It's the probability of excessive interference opportunity, or PEIO.
PEIO. Probability of excessive interference opportunity.
Yes, this measures the probability that the number of missed on-end channels, meaning channels that are actually busy with the primary user, but were mistakenly identified as free by the system, exceeds an allowed interference threshold, AIA.
So 8 is like the maximum number of mistakes you can tolerate making against the primary users.
Exactly. PIO-ID is the probability that pre-IO, where ID is the number of busy channels wrongly declared free. This is incredibly important because it quantifies the system's ability to protect those primary users from harmful interference.
So PISO measures if the SU gets enough, and PEIO measures if the PU is protected enough.
That's the crucial balance. You want low PISO, meaning you usually get enough channels, and low PEIO, meaning you rarely interfere with primary users. These two metrics together give a much better picture of WSS performance than just PEIF or PD alone.
And the paper we're looking at uses these PISO and PEIO metrics.
Yes. It doesn't just propose the new algorithms using rep-PC and ham-C. It also provides a truly rigorous theoretical analysis for all of them, deriving mathematical expressions for both PISO and PEIO under various conditions.
Theoretical analysis is great, But does it match reality?
That's always the question. And this is where they do the essential validation step. All of these theoretical analyses are then meticulously validated using extensive Monte Carlo simulations.
Running thousands or millions of virtual experiments.
Exactly. This is standard practice in robust scientific research. You run the system virtually many, many times with simulated random noise and channel conditions, and you measure the piezo and PEIO outcomes.
And what did they find? Did the theory match the simulations?
Yes, critically, they show plots where the theoretical curves, what the math predicts, closely overlap with the simulation results. This gives us strong confidence that their mathematical models accurately capture the real-world performance of these algorithms, including the effects of channel errors and coding. It means we can trust the conclusions drawn from the analysis.
Okay, so we have the right metrics, and the analysis seems solid. What do these measurements actually tell us about the performance, especially the impact of those imperfect reporting channels?
Well, first, looking at the baseline algorithm, the original PBNS CWSS without any error correction on the reporting channel.
The one that assumed perfect reporting.
Right. The experiments clearly demonstrate that its performance is greatly affected by reporting channel errors. It's not just a minor dip, it's a significant degradation in its ability to both find opportunities and protect primary users when P, the bit error probability on the reporting channel, is greater than 0.
Can they quantify that degradation?
Yes, the data shows a clear trend. As the probability of error P increases, the PBNS CWSS performance gets significantly worse. For instance, they show results where if you fix the acceptable interference level, PEIO, at 0.01,
Okay, a 1% chance of excessive interference.
the piezo value, the chance of not getting enough spectrum yourself, with a reporting channel error probability P error 0.15, is a substantial 17.22% higher than it is with P equals 0.0, a perfect channel.
Wow. So just a 15% chance of a bit flip on that reporting link makes you almost 20% more likely to fail in finding the spectrum you need.
That's what that specific result indicates. It really highlights just how critical, robust, error-corrected reporting channels are. Without fixing that weak link, the whole sophisticated sensing system becomes unreliable and much less effective.
Okay, so the baseline is vulnerable. Now for the real proof. How do the proposed channel-coded algorithms, RepC-CWSS and HAM-C-CWSS, stack up against that vulnerable baseline, especially when those reporting errors are present?
The results here are really the core of the paper's contribution, and they are compelling. Both of the proposed algorithms, RepC-CWSS and HAM-C-WSSS, significantly outperform the standard PBNS-CWSS algorithm when reporting channel errors exist.
Meaning lower piezo for the same PEIO, or vice versa.
Exactly. They achieve a much better trade-off between finding sufficient opportunities, low piezo, and protecting primary users, low PEIO.
And what about that error elimination idea with the repetition code?
This is where it gets truly remarkable. The paper shows that the RepC-CWSS algorithm, using a repetition length of just 3, R3, the minimum practical value,
Yes.
actually performs similarly to the original PBNS-CWSS algorithm operating under the ideal condition of no reporting channel errors at all. PEO equals 0.0.
Wait, seriously? R3 makes the noisy channel perform like a perfect channel.
In terms of the overall PESA-PO performance metric, yes, that's the huge takeaway. You can effectively cancel out the negative impact of those noisy reporting channels, making them behave almost perfectly from the system's perspective just by adding that simple R3 repetition.
That's incredible. It validates the power of even simple coding.
It really does. It's a powerful testament to the effectiveness of tackling that weak link directly.
Okay, so RepC-CWSS works incredibly well, basically restoring ideal performance. But we know it's inefficient. How does HAM-C-CWSS compare in performance?
This is the crucial comparison for practicality. The HAM-C-CWSS algorithm performs almost identically to the highly effective RepC-CWSS RD3 in terms of the PESA-PO trade-off.
Almost identically, so just as good at correcting errors and getting the job done.
Very nearly. They provide specific numbers. The piezo for RepC-CWSS R23 is only about 3% smaller than the piezo for HAM-C-CWSS at a PEIO target of 0.02. That's a tiny difference in performance.
Okay, so negligible performance difference.
But HAM-C-CWSS delivers that comparable performance while offering significantly reduced redundancy, as we discussed.
Lower bandwidth, faster processing.
Exactly. This makes HAM-C-CWSS the far more practical and, in most cases, the better suited solution for real-world deployment. It achieves essentially the same robustness as RE3 repetition, but with much greater efficiency. It's getting more bang for your buck in error correction.
That seems like a very clear conclusion. Hamming codes for the win, generally.
For this particular problem and the metrics used, HAM-CCWSS offers a very compelling balance of performance and efficiency.
Did the paper compare these proposed methods against any other existing techniques, like those OACWSS or one-bit FFT ones?
Yes, they did. They also compare their proposed REPC-CWSS and HAM-CCWSS algorithms against those other recently proposed state-of-the-art methods.
And how did they fare?
The results were quite striking here, too. Both REPC-CWSS and HAM-CCWSS outperform OACWSS and 1-bit FFT-CWSS according to their simulations using the PISO-PIO metrics.
By how much?
The numbers are significant. For example, at a target PEIO of 0.04, meaning a low tolerance for interference, the PISO achieved with HAM-C CWSS is reported as being 106.21% smaller than what OACWSS achieves and 65.86% smaller than what 1-bit FFT CWSS achieves.
Wow, that's not just better, that's massively better. More than double the performance compared to OACWSS in that scenario. Why such a big difference?
The paper suggests the reason lies in a fundamental difference in their decision-making philosophy. In REPC-CWSS and HAM-CCWSS, using the PBNS approach, decisions are made on only a few channels within the selected partial band.
Right, focusing on finding sufficient opportunities, SD, within the stand-L channels.
Exactly. The focus is pragmatic. Find enough good channels reliably.
Whereas the others?
The other methods, OACWSS and 1-bit FFT-CWSS, often attempt to make decisions on all channels across the entire wide frequency band they are sensing.
Trying to find every single opportunity.
That seems to be the goal. While this might seem like it would offer more potential free channels on the surface, this broader, less focused approach dramatically increases the chance of making mistakes, particularly causing interference to primary users, higher PEIO.
So, trying to grab everything leads to more errors.
It appears so. Trying to make decisions on every single channel across a wide band increases the likelihood of false positives, wrongly declaring a busy channel as free. This ultimately leads to inferior overall performance when measured by the crucial PEIO metric, which prioritizes protecting the primary users.
It's a classic case of less is more sometimes. Focusing on reliably finding what you need is better than greedily trying for everything and messing up.
That seems to be the lesson here. The focused PBNS approach, combined with robust error correction on the reporting channel, proves to be a more effective strategy for balancing the needs of secondary users with the protection of primary users.
The paper also looked at the impact of that PED parameter, right? The confirmation threshold at the fusion center.
Yes, Emma, the number of times a channel needs to be reported as free to be declared free. It's a vital knob you can turn to fine-tune the system's behavior.
And what do they find? How does changing VIC affect performance?
There's a clear trade-off. By increasing EMA, you significantly enhance the security against interference to primary users. You make it harder to declare a channel free.
Fewer false positives? Better protection for PUs.
Exactly. It's like requiring more yes votes from your scout team or more rigorous confirmation before you commit to using that lane. This provides a stronger shield for the incumbent licensed users.
But the trade-off must be.
The trade-off is that a higher FEN also naturally limits the availability of free channels for the secondary users because fewer potential opportunities will actually meet that stricter confirmation threshold. It's a tighter filter.
You gain security, but you might lose some opportunity.
Correct. The paper quantifies this improvement in protection. Increasing EFT improves the system's overall reliability against interference. For the HAM-C CWSS algorithm, for instance, they show that setting EFT equals 3 results in a PISO that is 25.03% smaller than when EFT equals 1 for a fixed, very low PEIO target of 0.003.
So requiring more confirmation significantly reduces the chance of the secondary user not finding enough spectrum while keeping interference extremely low.
Yes, it shows how carefully selecting and tuning EFT can significantly optimize the system's ability to provide sufficient spectrum opportunities for SUs while stringently protecting PUs from interference. It's a key design parameter for engineers implementing such a system.
And presumably other parameters matter too, like the number of channels in the partial band L or the number of cooperating users.
Absolutely. While the paper focused its plots on FD encoding, it's logical and generally true that increasing other parameters like L scanning a wider partial band or M having more cooperating scouts would also improve performance up to a point.
More eyes on the spectrum, more data points.
Usually leads to more robust and reliable decisions, assuming the system can handle the increased complexity and communication overhead. It's all part of that powerful concept of distributed intelligence.
The key, as we've seen, is making sure that intelligence isn't corrupted by the communication channel itself.
Precisely. That's where the error correction proved so vital.
Okay, let's try to wrap this up. We've covered a lot of ground in this deep dive. We started with that critical problem of spectrum scarcity, the crowded digital highway with valuable lanes sitting empty.
Mhm. And we saw how cooperative wideband spectrum sensing, especially when combined with the efficiency of partial band Nyquist sampling, PBNS, offers a dynamic, intelligent way to find those open lanes.
But then we hit the snag,
Mhm.
the real-world messiness of imperfect reporting channels, that static noise and signal loss that can completely undermine these sophisticated sensing systems if you don't account for it.
It's not enough to design brilliant sensing algorithms if the information they gather can't get to the decision maker reliably, like having the best scouts whose walkie-talkies keep cutting out.
And that led us to the solutions. The incredible power of error-correcting codes. We saw how simple repetition codes, REPSI, can work wonders, almost eliminating the channel error effects.
But then Hamming codes, HAMC, emerged as the more practical hero, offering robust error correction, almost identical in effectiveness to the best repetition codes shown.
But with significantly less overhead, less bandwidth needed, faster decisions, making them the clear winner for efficiency and practical deployment, and outperforming other state-of-the-art methods in the process.
This deep dive really highlights how these intricate, seemingly intractable challenges in wireless communication can often be tackled with clever, elegant algorithms combined with a deep fundamental understanding of information theory and channel realities.
It's not just about building faster radios, it's about making our whole digital world smarter, more efficient, less wasteful of precious resources, and much more resilient.
Exactly. This research pushes us closer to a future where spectrum is a truly dynamic, shared resource used much more effectively.
Absolutely. And it makes you think. As our wireless networks become ever more complex, constantly relying on this kind of dynamic resource allocation, whether it's for 6G, massive IoT, autonomous systems, maybe the principles we talked about today, like robust error correction for distributed intelligence facing imperfect information.
How might they apply elsewhere?
Right. What other channels in your life, maybe even beyond radio signals, might benefit from a bit of smart redundancy? Maybe not repeating everything 3 times, but perhaps some clever Hamming code-like check to ensure your most crucial messages, your most important insights, always get through cleanly and reliably, despite the noise.
That's a fascinating thought to ponder. How do we ensure reliable communication and decision-making in any complex system with imperfect information flow?
Something for all of us to think about as we navigate our own signals, both digital and otherwise.